Thank you, Fred. Ladies and gentlemen, welcome to this webinar where I'm going to talk about the MTBF and modeling system reliability. Now, first things first, for those veterans of my webinars and podcasts, you can see my voice is just a little bit different as I'm fighting a viral infection that my doctor informs me has no cure or medicine for. So just bear with me with my voice and I'll try and sound as unsickly as possible for the next hour or so. But what are we talking about in this webinar? Well, of course, we've got the MTBF, which is the second word of the title, and the last three words are modeling system reliability. Now, this is a conversation about what the MTBF is and is not when we're modeling components and how they behave to essentially create a system. And of course, we can't just launch into this conversation without making sure that everyone is on top of what the mean is. So the mean and the mean time between failure are some of the most overused concepts, metrics, terms, parameters, statistics in the world of reliability and quality engineering. And there's lots of reasons for why it is grossly overused. But before we get into what the mean time between failure is, we're going to do a bit of revision for some, and perhaps a gentle introduction for others in terms of what some of the underlying statistics actually looks like. And I'm going to go back to one of my favorites devices of all time, the ball bearing, which is a wonderful collection of parts to allow a shaft that's rotating at what can be high speed to be supported in a radial direction. Essentially, it means it allows a shaft to be held in place, which is very important for vehicles and ships and lots of other things where we rely on not usually electric motor, but electric motor or a gas or petrol powered motor to turn something really fast to make something amazing happen. Now, with ball bearings and everybody else's machines or products or items that they build, fortunately, failure is a random process, and our brains aren't naturally wired to deal with random things. In fact, I'll take that back. The conscious parts of our brain are not. The subconscious parts of our brain are. And that's why we're able to throw baseballs or guess time or have a few, do all the other things that our subconscious part of our psyche allows us to, those tasks that our subconscious part of our psyche allows us to complete as if it's instinctive, which is essentially what subconscious brain is all about. But when it comes time to using math and numbers, we are surprisingly amateurish as human beings when it comes to dealing with things that are random. And one of the first issues we have is that the technically minded people that we tend to be often facing scenarios where seemingly identical bearings have the temerity to fail at different times. And that is obviously the opposite of what our very scientific, deterministic, causal brains would like the world around us to behave. And so let's focus on what it means to be identical. The word identical is used a lot, and in many scenarios, that is a term whose shortcuts and local interpretations can serve us well. So we often use a term identical to describe two ball bearings like these two, which are perhaps taken out of the same box, obviously from the same model, from the same manufacturer, and we say these are identical bearings. But we also know, if we were to zoom in or have an absolute knowledge of these ball bearings, we know that perhaps the one on the left has an impurity, while the one on the right might have a dislocation. If we were to zoom in, so to speak, and examine the microscopic structure of the atoms and molecules that make up these two components. And so, of course, we all intuitively know that even though these two identical ball bearings are things we classify as identical 9 times out of 10, In practice, we know that if we were to zoom in enough, we'd see that they have some differences. And those differences are often in the form of defects that tend to drive how long each ball bearing is going to last. And so the term identical is used in scenarios where we know that these two ball bearings are not the same, but perhaps more correctly, indistinguishable. And if they're indistinguishable, that means we have to treat them identically anyway. So that means that if we have two things like two ball bearings for which we cannot distinguish between the two, and we use them in ways for which we cannot control the differences thereof, they will fail at different times. And we know that, which is the hallmarks of a random process. And so we'll bring in our random hand of failure, which summarizes all the different factors or uncertainties that drive the failure process of our ball bearing. Now, the random hand of failure will essentially control outputs, which in this case are going to be measured in terms of the time to failure. And it's common practice in the world of quality and reliability engineering to make sure that when we use the word time, we actually are referring to the units of measure that relate to how old our system, or in this case, ball bearing is. So in this case, time refers to the number of cycles that our ball bearing has turned. And our random hand of failure is going to essentially summarize all those different things that we know influence how long one ball bearing will last when compared to another. And you can actually see on the bottom right-hand corner, manufacturing defects, which we know exist, account for a precious tiny fraction of failures overall. If we treat our ball bearings well, they tend to last a very long time. And so our random hand of failure, which summarizes all that or represents all these different factors or uncertainties, will give us different outcomes for the seemingly same scenario, which is seemingly identical ball bearings being used in seemingly identical ways. And each one of these blue dots represents a data point that perhaps we gathered from a reliability test of a number of ball bearings. And each blue data point represents how long a single ball bearing lasted. And we have 100 blue dots or blue data points on the screen representing 100 ball bearings being tested until failure. Now, we often want to characterize the random nature of things to help us make better decisions moving forward, because just because something's random doesn't mean it's not predictable. So you can see straight away there is some sort of pattern with these blue dots. You can see they sort of coalesce or bunch up in at least one area, maybe to just slightly left of center. And in other areas, there is a scarcity of data points. Now, this is all well and good, but we are very visual creatures. And so one of the things we can do to help us understand or characterize this randomness is to use things, visual aids like a histogram. And a histogram, in this case, shows us the relative density of these data points. And this histogram shows us a lot more than just the sort of sense of density or clustering or coalescence of these data points along that horizontal axis. So this histogram starts to show more of a complete picture about the pattern of failure. And if we were to conduct a test where we tested an incredible number of data points, eventually our histogram would become so incredibly smooth that it creates a shape like this. Maybe we should call this the ultimate histogram. I'm going to color it, orange in this case. And so for those of you who've been involved in probability and statistics, you know that the curve at the top of this ultimate histogram shape has a name. It's called the probability density curve. And if this probability density curve aligns with how our primitive human brains would prefer to deal with characterizing randomness and uncertainty, we can look at this shape and we know very intuitively what this means. It means that where the shape is the highest, or the curve is the highest, I should say, the data points are more likely to have values at or around that region. And as the curve gets lower and lower, well, that represents those represent times to failure, which are less likely to be values that our data points will assume. So essentially, those blue data points are going to gather around the area where our probability density curve is the highest. And so, in a way, the probability density curve is the random process, or completely summarizes the random process that a random hand of failure is going to observe. And so when we go back to that test, you can see that the density of the data points, the clustering, tends to focus, like I said, around the region where the probability density curve is the highest. And now another way of visualizing this data is by, instead of looking at it in terms of just data points along the horizontal axis, if we were to add a vertical axis, where the vertical axis represents the percentage of things that have not failed during our test, or whatever process we went about getting these data points, we start to see a different pattern. So you can see that the percentage of things that haven't failed is always going to be 100% at the start of our test if we assume that we have all our ball bearings working. And as each ball bearing fails, we get a data point which slowly moves down as more and more things fail. Or in other words, the percentage of things that haven't failed decrease. And what this allows us to do is, if we were to get an incredible number of data points, we would eventually get this beautifully smooth line, the same way we get that beautifully smooth ultimate histogram shape, which describes the reliability of, in this case, our ball bearing with respect to time to failure. And every product has a reliability curve, even if we can't see it. And so this tells us, as our ball bearing ages, what the likelihood of that ball bearing still working is going to be. And you can see that there is some key characteristics of this reliability curve. Now we look at, you can see that the reliability curve starts at 100% as we assume, in many cases, things that we test are going to be working at the start of the test. But if that's not always the case, then the reliability curve doesn't start at 100%. And there are plenty of scenarios where that's the case. And we know that, for example, around about 15% of small satellites do not ever work after they're deployed. So we have what's called 15% dead on arrival failures. And you can see that our reliability curve is adjusted accordingly. It doesn't start at 100% anymore. It starts at 85% to take into consideration that 15% of our things have suffered dead on arrival failures. These are things that never work out of the box. Lots of reasons behind this. Perhaps the thing was damaged during the transit to your front door, or perhaps our small satellite was damaged during its often very violent transit from the surface of Earth to a low Earth orbit. So the reliability curve tells us an incredible amount of information, including if we have the overwhelming majority of things working at the start of the test, at the start of its useful life. And if that's the case, the reliability curve will start at 100%. But of course, reliability does not stay the same. You can see the curve does not have the same height. And so, for example, we can use this reliability curve to work out when we might expect 50% or half of our things to have failed. Now, in the world of ball bearings, this time has a symbol. We call it the B50 life. And we can see that the reliability curve tells us where this B50 life is by simply crossing the point where the height of that curve is 50. I'll describe that pretty poorly. When the height of that curve is 50%, that's the time by which we expect half our things to have failed. Now, see, Carl's asked us a couple of questions: random versus systemic or systematic fault. What's the difference? You'll have to go one step further, mate. You'll have to define what systematic is. A systematic fault is, in terms of quality and reliability taxonomy, It can be caused by lots of different root causes, and you'd have to really get to the root cause before you're able to say whether something is random or not. That said, as a rule, everything is random. There is no truly, we haven't been able to master with absolute certainty a deterministic view in the world of reliability engineering. We are getting better of saying it's likely for things to fail at certain times more than others. However, there's always that random nature. Now, we have a proposed definition for systematic faults. Systematic faults have a design issue behind them, and random ones have a root cause not depending on design issues, but is part of their nature. Well, I would push back on that, because if you have, for example, a design flaw with these ball bearings, let's just say the operating clearance between the steel balls and the inner races was not designed correctly for the temperature at which these ball bearings were intended to be operated at, then failure is still random. If you cannot predict with absolute certainty when that thing will fail, then it's still a random process. You might be able to say that improperly designed ball bearings will fail earlier than properly designed ball bearings. That doesn't mean that statement might be true and verifiable, but doesn't mean the failure of those ball bearings, defective or incorrectly designed or not, will not be random. And just because something is random doesn't mean it's not predictable. Peter suggests failure terminology, random in time, not by cause. Again, I'd argue absolutely everything is random in time. Again, if you cannot tell me the micro or millisecond by which something is going to fail, by definition, we call that random. Now, I understand there's lots of other terminologies out there where random is often used to describe like those environmental root causes of failure. And that, I would argue, is a misnomer. We know, for example, perfectly ball bearings that are operated in perfectly normal conditions, that are looked after, that are well maintained, which are well lubricated, will have a times of failure or reliability curve like the one you can see on the screen right now. So the term random is often used in a very colloquial way to refer to external or environmental stresses out of the norm, let's call it that. However, if you have no environmental stresses that are out of the norm, time to failure is still going to be entirely random. So hopefully that starts a conversation without providing distinct answers, because the term random has a very distinct meaning, but can mean lots of different things to different people. So let's go back to the B50 life and our reliability curve for this ball bearing, which is operating, let's just say, environmentally pristine conditions, but time to failure is still random. Now you can see that this point on our curve tells us we have a 50% failure probability or 50% reliability at the B50 life. And of course, as we keep using our ball bearing over time, the reliability will decrease to zero, because everything eventually fails, I should say. Now, as a rule, we're not interested in when the last, say, 90% of our ball bearings or other products fail, because by that stage, we have an obsolete system or a system that needs to be repaired. We're often way more interested in when the first small fraction of ball bearings will have failed. This can help us make really useful decisions. So, for example, if you want to service your machines and replace ball bearings before they fail, well, then you really need to understand the first part of this reliability curve. If you can tolerate no more than, let's just say, 1% of your ball bearings failing before servicing, then you are looking at the reliability curve with heights of 99% and more, and greater, I should say. So it's usually the first few small fraction of items that we're interested in understanding when it comes to reliability. Now, I see Carl writes that sometimes failure may be beneficial. Do go on. Any thoughts? Most of us want to avoid failure, but we can learn a lot from the experience. Failure can teach us what matters most to us and point to what we need to be successful. Failure is an opportunity for a fresh start. Yep, I think Anthony Robbins would say similar things in terms of in terms of self-help and motivation. And I'm not trying to be too facetious here, because we learn a lot from failure. And in terms of when it comes to reliability, we often want to push things to failure to understand how things can fail. But that should never, ever be at the expense of always trying to minimize the likelihood of failure when it matters in the future. Brian writes that that can be a difficult distinction in many cases. It prefers that designers completely understand all the stresses and can design for all of them. And often compromises are made due to space, cost reasons. Very few systems are designed to never fail. I'll push back on that, Brian. I think that any system that is designed to never, no system is designed to realistically never fail. We're talking about, we have fail-safe things, and we have concepts like that. But the reality is, designers, just because a designer doesn't know something doesn't mean they will not, does not then mean a mistake they make cannot therefore be classified as a design mistake. There are plenty of organizations where ignorance is not an excuse. Now, there comes a point where you don't want to individually model every single atom or molecule to the nth degree, because that's just a waste of time. You don't want to do that. But for things like pick on ball bearings, we know how to design good ball bearings. And even though we might be able to design a ball bearing perfectly with the right temperature profile for the RPMs and so on and so forth, failure is still going to be entirely random. And of course, Carl, not all failures are created equal. If you have a nuclear power plant exploding, that's one failure, which is a bad deal, versus perhaps some of the lights in the operating room short-circuiting. I know, again, that sounds like a facetious example, but in a way, or flippant example, it's not. We are always interested in the failures that matter the most. And in the scenario here, the first small fraction of things that have failed are the failures that matter the most for many design and maintenance decisions. So in the world of ball bearings, there is an industry term called the B10 life, which is used to sort of characterize the time by which we expect the first 10% of ball bearings to have failed. And if you don't use ball bearings, you replace the B with L to represent life, and we have the L10 and L50 lives for anything that's not a ball bearing. The ball bearing industry was sort of the first to coin or first to use these expressions, and lots of other industries said, that's awesome. We can't use B because our product or item doesn't start with the letter B in its title. So you can replace the letter B with L to describe any systems, describe the time by which you expect 10% of any system to have failed. And of course, there's a B10 life, there's a less common B5 life, the L5 life. You can make up whatever life that matters to you based on what your company or organization needs to do. And so if we go back to this reliability curve and then put it beneath that ultimate histogram shape we talked about earlier in this lesson, essentially, these two curves encode or describe exactly the same process, the same random process, but they do it in a very different way. How do they do that? The reliability curve is actually the curve that describes the right side area under the probability density curve. What am I talking about? Well, if we look at the reliability curve as it moves from left to right, you can see that as the dot that traces the reliability curve moves to where reliability drops to 90% in this case, that is also the point where, if you look at the area to the right of that time on the PDF or the ultimate histogram at the top, accounts for 90% of the area under that probability density curve. Calculus in the future, stand by. This is actually this calculus perspective is so high level that calculus is but a speck in the map or the journey we're about to undertake. So rest assured, there is not too many intimidating equations in this conversation we're about to have. But the reliability curve essentially traces out the right-hand side of the area under the probability density curve or the ultimate histogram shape, because both the area at the top and the height of our reliability curve represent the likelihood that something is still working. And as we move from left to right, we are able to continue tracing out. Sorry, I got ahead of myself. This case, this takes us the point where our reliability drops to the B10 life. Sorry for the amateurish delivery of this webinar. You can see is going to be given by a reliability curve. And if we keep going, we can find the point in time where we expect half our things to have failed, half our ball bearings to have failed by the time our reliability curve has dropped to 50%, which will also be where the right-hand area under our probability density curve is also equal to 50%. And we keep going and we completely trace out a reliability curve as we move from left to right. Essentially, as time goes by, things will eventually fail. Now, why did I torture at least some of you with this conversation about probability density curves and time to failure and and things like that? Simply because that's what we need to do. Well, my thing's got ahead of myself. Sorry about that. That's what we need to do to understand. Come on, computer, bear with me. The mean. The mean itself is simply the balance point of this ultimate histogram shape. The mean is where if we had turned an ultimate histogram shape into a physical three-dimensional shape with a mass, the mean, which we often represent with the Greek lowercase letter mu, is that balance point. That's all that mean time to failure and MTBF is. Sorry for getting my computer running away. I was obviously as excited as I am to learn about the mean. And this is one of the most important things that many reliability engineers are not taught about, at least to the length they need to be taught when it comes to doing probability and statistics and understanding what the MTBF can do to help us out. So for example, this is the ultimate histogram shape for the time to failure of a ball bearing. Let's look at the ultimate histogram shape for something completely different, like that small satellite we talked about earlier. You'll notice that the small satellite ultimate histogram shape is very different to the ultimate histogram shape describing the time to failure for our ball bearing. But the mean has not changed. The balance point has not changed. This probability density curve with the ultimate histogram shape does not naturally align with how we would like to visualize, as a rule, random processes. So this is when I say small satellite too, I mean really small satellite. Now, what is happening here is our ultimate histogram shape is hugging the vertical axis. And this might not look like it is possible to be perfectly balanced with most of the area of our ultimate histogram shape to the left, but rest assured, it is. And the reason it is because the ultimate histogram shape extends so far to the right that through essentially leverage, the center of gravity of this shape is perfectly located above the balance point you can see on the screen. Now, what causes this ultimate histogram shape? This ultimate histogram shape is caused by things that fail in a different way than our ball bearing, where you can see that for small satellites, they tend to fail very, very early in their operational life. And that's because they fail from wear-in or infant mortality, which is where a fraction of products carries problems that cause early failure. And those that are still working from a quirk of statistics, if they're still working, that infers that they are less likely to have one of those problems. And so they appear to become more reliable simply because they've already run the gauntlet of those early challenges that uncovered the problems that their sister and brother devices had. And so infant mortality is often caused by manufacturing defects, assembly or installation error, interface issues, software bugs, damage during transit and launch, lots of other root causes that will leave manufacturing defects, or let's just say problems in our devices. Now, people might say, well, that's just terrible. Small satellites, they clearly are manufactured to in a very defective way. But In the real world, small satellite manufacturing is quite challenging. They're not mass produced, they're job produced. They're often produced in batches of 3, 4, 5 at a time for new clients. There's often a big gap between manufacturing runs, and the components they use are designed for cell phones and lots of other devices which aren't ever designed to go into space. And so a perfectly well designed, a perfectly well manufactured small satellite will still fail in what appears to be a fingerprint of infant mortality, where manufacturing defects run riot, simply because the technology behind these products cause these sort of failures to be dominant. That of itself is of itself not a bad thing. It's just the signature of how these things fail. And like I said, the mean time to failure for our small satellites has not changed, because we have that ultimate histogram shape extending so far to the right that it creates that perfect balance. And unfortunately for small satellites, it means about 80% of things have failed by that balance point. 80% of small satellites will have failed by the time we reach that balance point. And then if we go back to our ball bearing, the figure is a lot closer to what we would intuitively expect, something closer to 55%. And if we were to look at something completely different, like a rubber tire, whose failure is based on more uniform wear out, where it results in this beautiful bell curve describing time to failure, then almost exactly half our things will fail by the mean time to failure. So there's lots of questions being asked. I'm going to have to come back to them before the end of this webinar to make sure we get off on some cover off, I should say, some key points. Now we can see with the balance point staying the same again for the rubber tire, we have a different fraction of things we expect to fail, even though again the mean time to failure hasn't changed. And if we look at, instead of things having problems at the start, when things wear out or things accumulate damage, we have a completely different signature for failure. And so the ball bearing itself and the rubber tire and lots of other things that we know accumulate damage, the probability density curve that describes their time to failure always, and I mean always, has a peak, regardless of what the shape of that peak looks like. If the probability density curve or ultimate histogram shape has a peak, and all you need to do is confirm if your thing is wearing out or not, then you don't need to do any more investigation. You know, whenever you see this characteristic peak on the ultimate histogram shape or the probability density curve for time to failure, your product is wearing out because it's accumulating damage through things like fatigue, where cracks grow slowly over time, oxidation, where things react with oxygen, corrosion, where that thing that reacts with oxygen is a metal, creep, where seemingly solid things infuriatingly deform slowly over time under stress, where we have a material abraded away, as is the case for our rubber tire, lubricant contamination, where particles and other things get in the oils and lubricants, which then trigger things like wear to be accelerated, diffusion, where conductive things in our electronic components have the temerity, or atoms of those conductive things in our electronic components have the temerity to slowly move throughout the silicon crystal over time. So anything that accumulates damage will fail in a very different way to our small satellites, and there's a signature on the probability density curve. And then if we look at how these things fail, we'll go back to the B10 or the L10 life, the time by which we expect 10% of our items to have failed. You can see that for this tire, with this probability density curve or ultimate histogram shape, our L10 life is just to the left of the balance point, or the mean, as you would expect. But if we instead look at the same probability density curve for a ball bearing, you see that our L10 life or our B10 life is now a lot further away from the mean or the balance point. Just to show you the comparison, even though the mean has not changed, the B10 and L10 life is very different. And when you look at the L10 life for a small satellite, well, good Lord, it is so close to zero that you cannot see that teeny tiny sliver on the left-hand side that represents 10% of the area under the ultimate or under the probability density curve, even though the mean time to failure has not changed. So the mean time to failure is not a failure-free period. You know, a lot of people say, of course, we know failure is not an option, but when we say mean time to failure, we sometimes talk about it being equivalent to a largely failure-free period. Again, mean time to failure is not even equivalent to that. The mean time, the only thing you can know about the mean time to failure is that it's the point by which you expect between 50 to 80% of your things to have failed. Now, why am I continuing to torture you with some of these statistics and math and everything else? Well, at least through pretty pictures, that is. Well, it's because it's very important when it comes to understanding the MTTF for a system that you are modeling, because there's lots of equations out there which give you the MTBF or the MTTF, depending on whether it's repairable or not, which mean practically nothing. And to understand why they mean nothing, we need to go back, continue this torture by putting in the random hand of failure again. Here it is for the small satellite. And we're going to add on the right-hand side a little, again, some of you people will have seen this before, sort of gauge where it sort of helps you visualize the extent to which the item that is creating these data points wears in versus wears out. You can see that this is the ultimate histogram shape for a small satellite, which we know wears in. And as we morph to perhaps the most extreme form of wear out, extreme in terms of, let's call it purity and how damage is accumulated, we get this beautiful bell curve like we see in the times to failure for things like rubber tires. And where wear is accumulated in a very uniform way. Now, Pete, I will address one comment here where Pete says the balance point of the PDF is the median, not the mean. Not so, Pete. The median is a point where you have 50% of your things already failing. And we know that, for example, the balance point of the times to failure for our small satellite is a point by which we expect 80% of our small satellites to have failed. So by definition, based on that example, that shows that the median and the balance point are certainly not the same. And so it's very important to understand those measures of central tendency for a term that's used as often as the mean. So let's now look at something which is neither wearing in nor wearing out, something right in the middle. And this is the ultimate histogram shape. Well, it's going out of control for me right now. This is the ultimate histogram shape of something that never wears in and never wears out. This particular ultimate histogram shape has a very key characteristic. Here you can see that the L50 life, which is the median peak, for example, so you can see the median is not the balance point for this particular ultimate histogram shape, has a particular characteristic for this ultimate histogram shape, which doesn't represent something which doesn't wear out or doesn't wear in. If I go the L50 life one more time, if I just take the same step to the right, well, the area in that interval I've just created is now 25% of the area under the probability density curve, or 50% of that area. And so what this means is that for every unit step I move forward, the percentage of things that is failing relative to the last batch of things which are still working always stays the same, and down to 12.5%. So every step forward you take, when we're talking about median or L50 life, we lose another half of our things to failure. This describes something which neither wears in nor wears out. These are things whose failure is caused by typically external environmental stresses, think tsunamis and tornadoes, human errors, And a very common one for electronic components is voltage spikes, where you have dirty power supplies and you have a 5,000 volt spike come through and ruin the day of the capacitor. That is the first thing to bear its brunt. Why are these the root causes for things that that fail, which in a way that don't wear out or don't wear in? Well, whenever these things come along, whether these environmental stresses come along, it doesn't matter how old or young your system is, it's going to have a bad day. A typical two-story suburban house will be absolutely obliterated by an F5 tornado. A 1,000 old, so let's just go a little bit more realistic. Let's say a 100-year-old cottage will also be obliterated by an F50 tornado, F5 tornado, I should say. And so whenever you have things fail where the root causes of those failures have nothing to do with the age of that device, that product, it doesn't matter how old or young it is, then you have things which are said to have what we call a constant hazard rate. Now, the constant hazard rate is, like I said, describes things that never wears out, and which means your device never accumulates damage, it never gets old, and it never wears in. And so it has no defects from the very start. And unfortunately, a lot of allegedly reputable reliability and quality engineering sources essentially say, regardless of this reality, we're going to treat things that we know wear in and or wear out as if they are modeled by this wonderfully simple ultimate histogram shape, which has these particular characteristics. Even though we know that tires and ball bearings wear out and small satellites wear in. And the reason this often happens is because this particular ultimate histogram shape is simple. Unfortunately, it's too simple. So we are going to get to a conversation about what this do with system reliability modeling. What we're going to look at right now is we're going to look at the random hand of failure for a pump. Now, we know from brutal experience and from our understanding, I got ahead of myself. When I say something is too simple, I should explain it in greater detail. I'm going to blame my illness for the amateurish delivery of this webinar. Hopefully, I won't be fired as a result. But the reason why this ultimate histogram is so simple is that the only thing we need to define it is the mean itself. The only thing that we need to describe this particular shaped curve is that balance point. So when the balance point is smaller or moves to the left, our shape adjusts accordingly, and as it moves to the right, it does the same thing again, which makes this a wonderfully simple ultimate histogram shape, but unfortunately, it is too simple. So let's go to that pump who's you got a sneak peek into with my amateurish delivery of said webinar for today. And the random hand of failure for this pump is obviously quite different to the random hand of failure for electronic components and lots of other things. And let's just say that we know through study and testing and what have you, that this bell-like shape here describes the times to failure, or the random nature, the times to failure of these pumps. And if we were to conduct a test, we would be able to learn something about where this balance point of this ultimate histogram shape might be, and that is the mean time to failure. So let's just say we test, in this case, I think this is 10. Is that 10 data points? Anyway, so around about 10 pumps are tested. And what you can see is we have what appears to be two balance points. We have a balance point on the right, which is actually the balance point for those 10 blue data points. Now, if anyone knows what this means, this is actually, or heard this term before, this is what we call the sample mean. The sample mean is a balance point of the data points we get through testing or whatever process we use to observe the times to failure of things like pumps. The sample mean is a balance point of the data points, and the true mean is a balance point of the ultimate histogram shape. And you can see they're sort of right next to each other. They're close to each other, but they're not exactly in the same location. What we can do, though, is get lots of data points, and and that sample mean we just talked about, if we get lots of data points, well, that sample mean becomes a much, much better or much, much closer to the true mean of the actual failure process for our pump. So let's start looking at a really simple system. In this case, we're going to look at a parallel system. Now, a parallel system is simply a system that fails when its first pump or first component fails. And so in this scenario, we now have two random hands of failure for pumps A and B. It's a parallel system. And the system fails when the last of these two pumps fail. And what we have now done is we've replaced the pump times to failure with grey dots and the system, two pump parallel system times to failure with green dots. And there's a green histogram here, which you can see tends to show that the mean or the balance point of the system times to failure is to the right of the balance point of the times to failure for the pump. Why is that? Well, parallel systems are more reliable. So you expect by having one redundant pump, the system's going to tend to last longer. And so you've seen the green data points for the system move to the right. You see the balance point of those data points move to the right as well. You can see in compared to the balance point of the times to failure for the individual pumps, yes, the mean time to failure for our parallel system is longer than the mean time to failure for a single pump, as you would expect. And that's a good thing, because when you have redundancy, you want to have something to show for it. But let's just say that for whatever reason, we were able to change these pumps or look after these pumps in a different way, such that the variation in these pumps' times to failure was reduced. That is, they're more clustered around their balance point, their mean time to failure. So let's look at what that does for the balance point of the times to failure for our system. So look very closely at what's about to happen on the horizontal axis, with the balance point for our green parallel system times to failure moves to be much closer to the balance point of our individual pumps. And so the key observation here is that you can never, under any circumstances, simply calculate the mean time to failure of your system based on the mean times to failure of your components. Even for something as simple as a two-pump parallel system, the way things fail, the shape of that ultimate histogram shape, the shape of that probability density curve, that is as important as anything else when it comes to trying to find the mean time to or mean time between failure for your system. The more spread out the times to failure for your components are, the bigger the impact it will be on system reliability and the system mean time to failure. And if we go the other way, so to speak, if we instead look at pumps whose times to failure are really spread out, you can see how far to the right the balance point of the times to failure for our parallel system are now. The mean time to failure for our pump hasn't changed, but the variation in those times to failure is now a lot higher. Again, you can see how big an impact it has on the balance point of our parallel system. And again, a parallel system is simply a system that fails when the last component fails. If we look at a series system, the only difference between a parallel system and a series system is that a series system fails when the first component fails. You can see the green data points to the green histogram are now to the left of the balance point for our pumps. That means that series systems fail when the first thing fails, tend to fail earlier than individual components. That makes a lot of sense, because if you have a series system with lots of components where if any one of those components fail, the system fails, you essentially give your system more ways to fail. And again, if we change the variation, the spread of the times to failure of our pumps or components, it has a huge impact on the mean time to failure of your series system. The less spread out those times to failure are, the closer the system mean time to failure is to the component mean time to failure. And so that, as I said, the system MTTF is not based on component MTTFs, which is one of the biggest things that is omitted from many system reliability modeling courses. So, for example, we have this series system here, which is modeled with with fault trees that are based on OR gates. You will find textbooks that tell you that the mean time to failure of this series system is given by this equation, where the mean time to failure of each component, or the ith component, is represented by this symbol embedded in that equation. So how can these scandalous textbooks and guidebooks make this claim that you can get the mean time to failure of the system based on the mean time to failure of the components? Well, this will only ever be the case if your components have constant hazard rates, i.e. if your pumps never wear out and never wear in. For parallel systems, you will have those same scandalous textbooks tell you that the mean time to failure for our parallel system is given by this equation here. Now, when we have parallel systems, as a rule, when we have redundancy, the redundant component is usually similar to or identical with to the primary component. So you often see components in parallel systems be identical, and they tend to have the same MTTF. And so you'll often see this expression here, where if you assume those components have the same MTTF, then the MTTF of a parallel system for n components is given by this expression. And that is only true if these pumps have the same constant hazard rate. Again, this is not common knowledge, or not sort of widely published when it comes to those textbooks and guidebooks which tell you what the MTTF is. Now, there's one more system we need to concern ourselves about, and that is the K out of N system, where the system only works when K or more of these components are working. The expression for the MTTF of this system, you will see in those guidebooks and textbooks, is very similar to that of the parallel system. It's just that instead of starting at 1, it starts at 1 over K, remembering that K is the number of components that need to work for your system to work. And so you often get these three equations sort of presented in tabular form to give you the MTTF of your system for different system configurations. However, this is only the case if every single one of your components has a constant hazard rate. And as a rule, precious few, and I mean an exceedingly precious few things, have a constant hazard rate. It is the reason why we are often drawn to make this constant hazard rate assumption, is that it gives us simple equations like this to put into a report to get a number to describe the MTTF of your system. And it is simply not the case. What you need to do is what I did when I used those random hands of failure. We simply need to find the probability density curves of the times to failure for your components, and essentially create hundreds, thousands, millions of data points that then give rise to us understanding when those systems were going to fail. And you find the balance point of those hundreds of thousands of data points to get your system MTTF. And it's really important to do that, because these equations that give you these spurious MTTFs for your system are going to be violently wrong for most real-world systems, where components either wear in, wear out, or have a combination of both. In fact, by doing things the right way, by understanding your system MTTF, you might actually get the number you need to demonstrate to meet the reliability requirements of that system. If you use these equations, you might get a number which is 1, incorrect, and 2, below your requirements. And so understanding that you need to essentially replicate those random hands of failure to get your system times to failure and find the balance point of those data points, it might save you months or years of remediation that you didn't have to do. But perhaps my most important message for today is that the MTTF is not the failure-free period that a lot of people tend to think it is. It's not even equivalent to a largely failure-free period. Anywhere between 50 and 80% of your things have failed by the MTTF. Oh, so let's go back to that last slide, because I think that's a nice slide to finish the conversation on today before I launch into this novel of questions that I have been casually observing as compiling in the chat window. So let's see, what have I not answered yet? Right, so Carl writes, the slogan, fail in order to succeed sooner, would hardly promote success in a manufacturing plant. Any thoughts? Again, I'm always careful with slogans. Slogans can be interpreted in many ways. For example, there's a saying which says you've got to spend money to make money. Yeah, a lot of people have had fun with that. Because you want to induce failures in the right way. Often when you have those initial low rate production runs, that's when you want to have those edge conditions to see what your system's going to do when you have less than ideal input parameters, so to speak. So yes, you want to understand failures, and that often one of the best ways of doing that is by pushing your thing to its limits and beyond to create failures. But you can do that in a very controlled way to learn how to prevent failures later on. James writes that he likes that epic fit. Thank you very much for that, James. Much appreciated. Back to Carl. Once a fire has been detected, it is essential to go beyond the obvious and superficial reasons to understand its root causes. I'm going to stop that one right there because you're 100% right. But that's a root cause analysis commentary that fills the rest of that comment there. You're not wrong. It's just that essentially we should not leap to conclusions. We should always scratch the surface and work out what causes failures, because if you don't do that, you won't be able to remedy them or remove or change the likelihood of them happening in the future. And yes, leadership is very, very important. And Dan writes, and also not to stop looking after finding one failure. You may have another weakness ready to cause an issue. Beautiful. Love that message. We should be not afraid to look for bad news. The more bad news we find now, the more crises we save later on. Sanjeev writes, do all infant mortality defects have human error as a cause? No, definitely not. A lot of them do. But when it comes to small satellites, for example, I would argue that you'd be very cruel to describe the challenges they have in manufacturing small satellites as human errors. Yes, they don't have a lot of really mature or experienced manufacturing technicians, but that is because, like I said, they have a lot of small production runs. They have often very tailored to specific clients. They have to use components designed for other industries and technologies and operating scenarios. And so you often have, let's say, design engineers who put on the hat as manufacturing engineers when they have to build these 3 or 4 or 5 small satellites for a particular customer. Until they have the ability to support mass production, they can't have all those wonderful quality initiatives that work well in in facilities that are able to leverage mass production. Now, that doesn't mean that infant mortality does not have human error as a cause. That there are quite cases of infant mortality, sorry, I'm going to start that sentence again. There are clearly cases of infant mortality where human error is a root cause, but it's certainly not a given, so to speak. You're also right that time to failure for reliability calculations are for the first failure, while MTBF is used for availability calculations. Is that correct? Yes, availability is often based on the MTBF because that's a whole nother conversation, but the MTBF, in a way, it works beautifully when you add things up. So you have the MTBF, the mean time to failure, which also represents the mean time your thing works. Then you have the mean downtime or the mean time to repair or mean corrective maintenance times, etc., etc., etc. But of course, the MTBF only works if, for availability, if the only reason you have downtime is due to corrective maintenance. because MTBF plus mean corrective maintenance time, or mean time to repair, is essentially the operating time from that perspective. So MTBF can be used for availability calculations, but as soon as you use it, you're sort of constraining yourself to only considering downtime to be caused by repair. I've touched base on the balance point being the not being the medium, and hopefully some of the visuals have illustrated that. Charles writes that electronic systems need to perform margin testing as part of the reliability testing to flush out weaknesses. Absolutely, there's a couple of rules of thumb when it comes to electronics. Electronics are classic candidates for, say, problems which cause infant mortality or wear in. And that comes down to the fact that the silicon chip that a lot of electronics are based on, it's not a perfect manufacturing process. The world's best approach to creating silicon wafers, which would ideally be a single crystal, will still have unavoidable defects from time to time, and those defects will manifest themselves in terms of infant mortality or wear and failure. Aaron writes, what is the right approach to calculate system MTTF? Like I said, Aaron, you need to, there's lots of different ways. A theoretical way is very, very challenging. The simplest way is to simply simulate times to failure for your components like we did for the parallel and series system, and then create for those simulated times the time to failure for the system itself, which will be based on the combinations of different component failure times. And when you find that data point, lock that one away, do that several times over, and find the balance point of those mean times to failure. And do that a lot, and computers can help, and that balance point will become a really good estimate of your system MTTF. Ajit writes, speaking to the MTTF formulas, what if you don't have many samples to test, but only one or two? Well, I can't tell you if that's going to work or not, because sometimes I need to know what decision you're trying to inform, Ajit. Sometimes if you just need to understand if your thing's going to last more than a year, one or two samples are all you need. But if you only have one or two samples without being able to say this is a guaranteed way of working for you, if you know that you have a ball bearing, for example, where you have one or two times to failure, we know that for ball bearings, the Weibull distribution with a shape parameter of around about 1.5 tends to do a pretty good job of describing the shape of the ultimate histogram shape that describes time to failure for that component. So do a bit of research. You know, tires, for example, things that wear out at a uniform rate, times to failure, by definition, will be described by that beautiful bell curve. So if you're able to do a little bit of critical thinking to work out what causes your failure, and then work out which probability density curve is the right one for that particular type of failure, then you could potentially get away with 2 to 3 samples. If you essentially assume things have a constant hazard rate because you only have 2 or 3 samples, then you're in trouble. And that's where one webinar I suggest you look at is my webinar regarding Y-Bays, where essentially the shape parameter of the Weibull distribution can become the fingerprint, so to speak, of different failure mechanisms and the times to failure of specific components. Samantha writes, when suppliers give an MTTF for the component without also giving the probability distribution, how can we generate the necessary distributions to perform adequate modeling? Okay, so Samantha, one option is, like I just said, where let's just say your supplier is a ball bearing manufacturer. That said, ball bearing manufacturers tend to be pretty good at giving you more than scant information regarding time to failure for their devices. But you have to get that information from somewhere. Again, how much confidence do you need to make a decision? If you're happy to do a literature review to understand that the tire will wear out with the bell curve, fantastic. But if you if the decision you are making is, let's just say, critical, or whatever that means, or you need to have a very precise understanding of system reliability, then you need to go one step further. However, Fred and I had a conversation about a person I met, or didn't met, but I had a conversation with Rams conference earlier this year, where he was struggling with the same scenario for the for a DC converter for the machine he was manufacturing. Long story short, he had 3 suppliers. He was able to, with his basic testing, 1 or 2 failures for each component, he was able to work out, well, these times to fail were essentially 3 times longer than the service duration or the service life of the machine. Long story short, those things were not going to cause that machine to ever fail. So wherever possible, find those components which you know are either not going to or are highly unlikely to cause failure, will result in failure for your machine because their times to failure are suitably long enough for your applications, and then don't worry about modeling them. So you can be sort of very, apply a level of triage, so to speak, to some of these components. And I hope that goes some way to answering your question. If not, feel free to reach out and we can keep this conversation going. Carl writes, types of human error include all those things. My thoughts are, yes, they do. And those human errors include lots of those things. They also include those design engineers who just add a tolerance of plus or minus 10% without thinking about whether that tolerance is the right tolerance for the manufacturing team. Thanks, David. Much appreciated. Let's see. Got a lot of thanks now. I think people need to go to have their lunch or breakfast or whatever it is they're doing in their part of the world. Thank you for your thanks. James writes, how would you define reliability at lower confidence bound in a layman's term, realistic or pessimistic estimation? So firstly, confidence is a measure of you. It's not a measure of your product. So if you need to be really confident, then you will have a lower confidence bound on reliability as a number where you are really, really confident that the true reliability is higher than, or is higher than. And so that means that the more confidence you need from a statistical perspective, it sort of drives down that number you use to represent your lower confidence bound. If you just need a rough guess, or the decision doesn't need a ton of confidence, then your lower confidence bound will be a lot higher, because you only need to be sort of confident that the true reliability is greater than that data point. I don't know if that satisfies your definition of lower confidence bound, but if you're going to explain that to anybody else, what I always do is say, just remember, confidence is a measure of you, not a measure of your system. If you need a lot of confidence, then your confidence bound will be extraordinarily pessimistic. Let's use one of the terms you put your way. If you only need some confidence, then it's going to be less pessimistic. I wouldn't call it optimistic, but it's because it's still an element of pessimism with a lower confidence bound. But it's going to tend to be closer to the true value if you had enough information to ever find that out. Thank you for your thanks. And I just emphasize what Fred's saying about standards and databases. They do assume constant hazard rates, which is one of the issues we have. Jonathan writes, for a parallel system, is the hazard rate constant? Or in other words, can the hazard rate of the parallel system be calculated as 1 over the MTTF of the system? I'm going to throw that question your way, Jonathan. Do the components in your parallel system you're alluding to never wear in, never wear out? Because if they don't, use that equation. If they do, then by definition, the parallel system cannot have a constant hazard rate. See, there's conversation about databases and data going on. Fred's retorting with the fact that the supply is not the only source of information. Again, if you were to rely on electronic components manufacturers and suppliers, they often use this term called failures in time, or FITS, which represents 1 failure per billion hours. Anyone who knows how those people test the reliability of those components, they only test those components a very short window of their operational time, maybe for 100 or 1,000 hours. But we all know electronic components will wear out through dendritic growth or diffusion. And so you'll often be given fantastic fits as in phase and time numbers from electronic component suppliers. Some which have as values as low as 100 fits implied the mean time to failure of their components is over 11,000 years. So you can't just take numbers blindly from manufacturers or suppliers. And in the real world, because customers aren't really demanding a change to how those manufacturers provide electronic component reliability characteristics, they're going to continue to use fits. And there's no incentive for one manufacturer to deviate from that process because that will automatically to those ill-informed parts purchases for different companies across the world, they'll automatically see a number which is different and worse and go with somebody else who still uses the old fits approach. So you can get upset by that or frustrated by that, or you can just accept it as reality. And that means you really need to understand the times of failure for electronic components beyond the numbers that are given to you by your suppliers. Thank you for your thanks. Any more questions? Oh, Cliff from Sydney, 3 a.m. Good work, Cliff. Much appreciated for you putting in some hard yards. What should we do during project design phase for conducting reliability prediction for components as there are no supplier data? Cliff, now reliability prediction is a very dirty phrase in the world of reliability because reliability prediction often refers to scenarios where you have existing tables which give you indicative times or mean times to failure or failure rates for different components with different technologies from different industries. The reality is that when it comes to the project design phase, you should not be predicting the reliability of something which hasn't been designed yet. I know the systems engineering approach often makes us think we have to have these numbers up and running, but the reality is a lot of the really reliable things out there are built and designed without having to come up with numbers during design. What does that mean for you? If you are going to have like the classic FMEA approach, and a good FMEA is a great FMEA, there are terrible FMEAs as well, but that's where you use subjective assessment to work out what things are going to keep you up at night when it comes to failure that you can address during design. And once you've done that, then you should have a list of the vital few things that are going to cause your system to fail one day, and those are the things that you model with great accuracy and fidelity. But reliability prediction, in terms of the way I described it, where you just look up a table and say, okay, resistor, mean time to failure of X, put that into a model, get a number at the end. That has been proven time and time again to be a waste of time because it describes, at best, a system which is at least 5 years old based on numbers that were sort of sourced from the very few companies that were willing to share their failure data, et cetera, et cetera, et cetera. Yeah, that might not solve your problem because in your project design phase, you might be working for a client or a boss or an organization that demands those numbers. I don't have good news for you because reliability prediction is almost always a waste of time during design. So I've answered that question from Jonathan over here. Thank you, Carl. Cliff, let me know if I've come close to answering your question, if we need to talk more. Let's see. Bert writes, those 1,000-hour tests are run at elevated temperature to accelerate the test. If you're talking about electronic components, that's cool. However, with what we know about those electronic components, we know that no electronic components will last 11,000 years, but we still have electronic components with fit rates as low as 100. So regardless of any attempt to make those tests valid, the numbers that we routinely get when we even do a Google search for reliable electronic components, where you get 100 fits, for example, are clearly meaningless. So the test is invalid. if we're getting numbers that suggest the average component or average capacitor will last 11,000 years. Just to be clear, capacitors as a concept have not been around for 11,000 years. Brian, great presentation. Oh, I'll read the next bit. Maybe consider taking this a step further and work out examples and tell versus show. Fair, Paul. One of the things I'm going to be looking at is a layperson's approach to Monte Carlo simulation, which is something I alluded to with those random hands of failure, I should say, dropping those balls. And that might be one great vehicle to show you how to do this. I often find though that when I do Monte Carlo simulation webinars or lessons, I need to spend more time than people would like on sort of understanding the fundamentals of the concepts, like what MTTF for a system is not. But I do take your point, so we might look at scheduling something like that in the future. Samantha, even if doing a reliability prediction as a basis to Bayesian analysis with probability distributions that set as discrete values, I could see that, Samantha. Again, all these questions, all these scenarios, if we knew what the decision was, which I know you probably know what decision you have in mind for these scenarios where you're using Bayesian analysis, then you could sort of more, I could probably perhaps more forcefully answer those questions. One of the biggest problems I've observed, I should say, as a reliability engineer, is as soon as there is a number put next to that component's name in a spreadsheet, that is it. It never gets revisited. There's a number there. We're done. We stop thinking about it because the failure rate for the component we identified at the start of the design phase was one failure per 10,000 hours or whatever it is. As soon as that becomes a number in a spreadsheet, we're done. Now, if you're doing Bayesian analysis, there's a chance that your organization actually has a sort of more holistic approach to understanding times to failure and random processes and things like that. There's a good chance that those numbers won't be cemented over time. Again, if you're trying to get a general idea of the reliability of your system, then Bayesian analysis could be really, really useful. However, I would suggest that quantitative reliability analysis is often premature when you are trying to sort of make it happen as part of your design. We know, for example, about half of all failures occur at interfaces between components. So components that work perfectly well can still cause failures when one creates excessive heat and sort of takes out a component next to it that we didn't think about, or one is expecting torque to be entered as a data value in terms of foot-pounds, but instead that value is entered in terms of Newton meters, where again the components work perfectly well, but the way they interface causes failures. And so I'd always recommend that we be very subjective, at least during the start of our design process, to make sure we think of all these things, design those root causes out of our system. The earlier you do that, those design changes are often fast, simple, and free. Simply moving the hot component away from the temperature sensitive one is something you can do in a heartbeat during your initial sort of design where you haven't built any prototypes yet. Once that temperature sensitive component is next to that hot component in an engine bay, now you need to retrofit insulation and all sorts of other things. That becomes an expensive problem. And so what you should be doing during the design phase is to come up with that never-ending list of the vital few weak points. And then once you have that, never-ending list should be a never-ending challenge. It should be a small list once you get there. And then those vital few things, the ones you invest time and money into modeling. Charles writes, what about if the vendor gives you fit test data and they start that 24 parts tested at X acceleration values with no failures, and they start a fit of 11? Hard to push back. It is just a point failure. But typically when I look at the RMA history, we always see a few failures of the devices from our database, thus update the failure rates. agree fit is very questionable. So for example, let's just, I'm going to do the math. If you have a fit rate of 11, I'm doing it on the in Excel right now. So that means we're having 11 failures per 1 billion hours. So the mean time to failure is a very, very big number. I'm going to turn it into days. Still an incredible number of days. Turn that into years. Bear with me. I just think it's a useful real world example. So for example, yeah, that means a fit rate of 11 implies the mean time to failure is 10,370 years. It's just not a thing. The reason why you can push back is because what is happening when these vendors test their things is they're testing their things before enough damage has been accumulated to create failure. So you can accelerate as much as you want, but if that acceleration factor still doesn't explore the times when enough damage is accumulated, then you'll still get these fantastic fit rates. And for things that wear out, it's like saying, well, let's test 1,000 tires for 10 kilometers or 1,000,000 tires for 10 kilometers. That's a total of 10 million kilometers. And you would expect to have precious few failures. It's no point in having those tests because you're not removing enough tread to explore the failure mechanism. And you can say, well, we had an acceleration factor for those tires. We doubled the mass of the vehicle that was driving those tires, those 10 kilometers. And that was an acceleration factor of 100. Okay, so 10 kilometers is equivalent to 100 kilometers in the real, 1,000 kilometers in the real world. Still, virtually every tire we know of is going to last way longer than 1,000 kilometers. It doesn't matter what the acceleration factor is. If you don't explore the failure mechanism of your device, then you're not really gathering valid data. That's what it means. And so, I mean, it's hard to push back with vendor suppliers because they're so used to defending any challenges to the almighty fit. In the real world, you need to understand those numbers are borderline meaningless and work out what you need to do for your device. Now, sometimes you can get around this by simply having a derating policy where instead of using something that's rated to experience 5 volts worth of typical voltage, you use something which is rated to experience 10 volts. And that can have a drastic improvement on life in a very qualitative way to the extent that you might satisfy yourself that capacitor is no longer going to fail during the service life of your machine, and therefore it stops being on your list of the vital few, et cetera, et cetera, et cetera.
Yeah, Chris, I'm going to jump in on the supplier thing. Is instead of stopping at, I mean, and I've run into this so many times. I call a vendor and say, hey, how's the reliability of your component? And they give me a fit number. I says, well, that's great. How does it fail in my application? And they go, oh, it'll never fail. I like, bullshit. Pardon my French. It's no. What is the most likely failure mechanism for your product in my application? And if the person on the phone can't answer it, call the CEO, call the director of engineering, get somebody that actually is honest with you. And then you get some information about a failure mechanism. It might be diffusion, it might be corrosion, it might be this or that or the other thing. Now you've got a clue of where to go to sort out, well, what's the likely scenarios that's going to happen in my application. But if you just stop at, well, the only thing they give me is fit, and they give me fit data on a meaningless test. Well, what failure mechanism was this test designed for? So if they accelerate with temperature, but it has nothing to do with 3-point bending, which is how it's most likely to fail, then it's a meaningless test just by design. So I always ask, how will it fail? It will fail at some point. You have experienced failures. What's likely to fail? And then that leads to a much more useful discussion than looking at a data sheet.
Concur. And thanks for saving my voice.
Yeah, no problem. I know you've been working your way through it. Lots of questions today. This is amazing.
I know. I think I said I got a sore voice or croaky throat, and people said, "Ha ha ha!
I gotta make
Watch
them
this."
talk an extra half
Yeah.
hour. Yeah.
Excuse me. Ah. Oh, thanks, Samantha and Bert. Um, but yeah,
Oh, hey, I
hopefully
got
we.
included in that one. Cool. Yeah,
Oh, you are awesome, Fred.
yeah, thank you.
But
Uh,
I actually think I have a webinar later on this year regarding Monte Carlo simulation. Let me
yeah, I
just.
think you put it in there. I think this is the year of system modeling, so looking forward to the sequence.
Yeah, let me just double check. Maybe I can answer the question right now. What's the next one? Maybe we should do that the next webinar.
Well, you better tell me today because I'm going to start promoting it this afternoon.
Let's do that. Let's
Right.
do it
Send
right
me a
now.
note.
Lock
Send
it
me a
in.
note. You're going to do which one is, it's already in the queue, right?
Yeah, it's the August one. We'll move the August one to April.
Okay. And I'll move the April one to August.
Mm,
Come on, make my
done.
life simple here.
Done.
August and April. All right.
Right.
All right. Well, I think folks have either left us hanging on their window and they're in another meeting somewhere, or they're still listening. But either way, thanks for attending. Let's spare Chris's voice a little bit here and say thanks for all the questions and all the inputs and enjoying the random hand of failure. It is a great concept. Great.